the negative here and see you on. Okay, so I'm going to talk about stability of toric vector bundle, and I will highlight this in two cases where we understand stability quite well. In other cases, we don't understand it so well, so this is an advertising talk for you to work on this and see whether you can add something to the story. Okay, so let's first start with what stability I actually mean. I mean Mumford, Matsumoto, or slope stability here. Okay, so in our setting here, we'll assume that X is a projective variety. Many things of the story, of course, generalize to much more general cases, but then some of the definitions become maybe a little bit different. Not as easy to compute. So let's keep to this. So D is an ample divisor. On X, and E is reflexive sheaf. So here you can also take covariant sheaf. Then you can define the slope of E. So this is usually denoted mu. Then you can sometimes we write the D if we want to make sure that we remember with respect to which line model we take the slope of E. So this is the first turn class of E. Tensor times B to the dimension of X.
Milena, can you remind us of the definition of reflexive?
Yes, so reflexive means that E, so you have a natural map from E to the double dual. So this is E dual all X, and you want this to be reflexive. If this natural map is an isomorphism.
Is there like a standard example to have in mind for this property?
Vector bundles.
Sure, but
value generalize idea sheets.
Okay.
I
don't think they have to be general reflexive.
No, of course.
I have them in the Toric language. But,
okay, we'll see
let
then.
me see. Yeah, I mean, for example, the tangent sheaf, like that'll come up actually. So if you have X, smooth, not smooth, right? Then you can still define the tangent sheaf, and that's going to be a reflexive sheaf.
Okay.
This is an example. And then divided by the rank of E. So here C1 of E you can compute as follows. At least for a vector bundle. So if E is vector bundle, of rank R, then C1 of E is C1 of the R determinant of E, and this is going to be some O of EE, some divisor, so this term passes. So that is a slope. And let me say that E is stable, is semi-stable if for all reflexive subsheaves F in E, we have mu of F is less than in the stable case or less than or equal to in the semi-stable case. Have that inequality of slopes. And so it turns out that this definition, if you have a vector bundle and you somehow want to find a moduli space of vector bundles that are similar to this, then this turns out to be the right definition to get a nice moduli space. So originally this comes from the IT, and yeah. So if you want to form, this is where this comes from, is you want to build moduli spaces of vector bundles, and that is the good definition to do that. So, but yeah, we're not going to do moduli spaces today. So. In general, it can be just difficult to write down stable sheets. So I give you an ample divisor and I tell you, can you please give me a stable sheet for this divisor? That I will give you an answer to this now, but I mean, this is sort of not so easy. And for example, it's also difficult question to understand for which term classes there exist stable sheets. So this is answered in P2 and the tensor surfaces. But yeah, so these are sort of questions there. So one answer to writing down a stable sheet with respect to polarization are syzygy bundles.
I have one question.
Yes.
For this definition, the mu depends on it's for all D or all non-divisors, or is it just for one fixed number divisor?
That is fixed. So we always fix this. So this is a polarization. So you wanted to okay, so what are syzygy bundles? So if you have all of D globally generated, then we define and make it a short exact sequence. So if it's globally generated, this means by definition that we have a surjection from the global sections of all of D onto all of D. And we can take the kernel. So we call this empty. And so this is called the syzygy bundle because this bundle and exterior powers, tensor, powers of D tell you about the Betti numbers of the embedding of D. In this case, this is very ample. So this is this is related to algebra here. And so the theorem is the following. So this gives you a stable sheet. So this is due to Einladungsort. Muss sogar 14 and 13, and the dimension of x is equal to 2. And Krikuski and arbitrary dimension. So M, the Syzygy bundle associated to a high multiple of this P is stable with respect to. And this is for M very large. So because he has an effective bound here, okay, so at least we can write down some stable bundle with respect to this polarization. But in some sense, this is, of course, a very crude answer because this has high rank and, you know, just one given turn class. So, but at least it's something, right? I mean, you can't say anything about, we can't say anything like this must have like a stable bundle of rank 2 or something. And so in this article, Lazarsfeld and Mustopak, they also asked a question. Does the same thing hold with respect to arbitrary polarizations? So can we exchange the D here by an A? And that turns out to be false. And so that's a small contribution by us, but I think it was important because like there were a few archive preprints claiming this, and also like some stuff in the literature that our example as a counterexample too. So I thought it's good to know. So the problem is so here A is not equal to B. And the composition is, so this is joined with Goethe and Katharina Jochen and Henrik Süß. Okay, so here's the example. So if X is the blow up, so this is very simple, but it was still not easy to find. And we take E, the exceptional divisor, and H, the hyperplane divisor. Then for D equal to 6H minus E, and M greater than 17, we have M of MD is not semi-stable. with respect to minus kx, which is in this case 3h minus k. And the destabilizing subbundle is again a kernel bundle. Or a destabilizing subbundle. Is M of O of MD minus B. Okay. So yeah, that's somehow bad news. So then you can ask, the more refined questions: for which line bundles A is MD stable for M very large? But yeah, we don't. We have an answer to this in this particular case. And so the way we do this is actually we have translated this in the toric case, so the blow up of a point in the projected plane is a toric variety, and in the toric case, this kernel bundle is what's called a toric vector bundle. I'll talk about them more later. And we have translated the condition for this to be stable in a combinatorial condition. And we actually can show in the toric case, at least, that it is enough to check subbundles of this form in order to check stability. And yeah, so this came through this combinatorial picture. So I won't go into this because these bundles are just a little bit bitchy and complicated, but not that simple. Okay, so the next class, are there any questions about this? I'm going to change this a little bit. Okay, so if you don't like syzygy bundles, you might like tangent bundles. So now we're going to talk about tangent bundles. So for tangent bundles, so when X is of general type, and or X is Calabi-Yau, so this means that the canonical device is positive, it's ample, and here this means that the canonical device is numerically equivalent to 0. Then we know that Tx is fully stable. So I didn't tell you what fully stable means, so this means it's a direct sum of stables with the same so we know a lot. If X is Fano, then we don't know. I mean, we know lots of special cases, but in general, it's a bit chaotic what happens. So whether the tangent bundle is stable or not in that case. So Fano means minus kx. So there's the reason we know this is there's a connection to Keller-Einstein matrix. And I'm not an expert of that, but I just wanted to tell you that, you know, like you have this theorem. So if X has admits a Taylor Einstein metric, then there's a theorem by Kobayashi and Lee. So these are independent theorems. And here it's fully stable. And now this follows from like the big great theorems on Taylor Einstein metric. So this is Auburn and Yao, and this is Yao, I think. And here I will talk about this a little bit more later. Now actually, so that is in the bottom case. So we have Chen and Donaldson and Saxon, and they say that if X is Kano, then X admits Taylor Einstein metric. If and only if X is K stable. So K stable is a different stable. So this is we somehow look at test configurations and some invariance there. And then you can say, so earlier this kind of theorem has motivated a lot of research on checking whether tangent bundles are stable or not. And then you could say, well, now we know this theorem, and why do we still want to do this? But I claim this is still very difficult to compute. So I think you still can get information about Taylor Einstein metrics, possibly by, or when they, at least when they don't exist, if you
To be on the safe side, X admitting a Taylor Einstein metric means that the tangent bundle of X admits a Taylor.
Yeah. You're lucky enough to understand what that means.
Sure.
With the Taylor Einstein metric. I mean, it's sort of a very regular metric. It's like very. Okay, so we worked on this for toric varieties. So here's one theorem. Well, it's just toric surfaces, but it was not completely trivial. So F is a toric surface. Then there exists
Okay.
ample polarization such that Tx is UV stable if and only if X is an iterated blowout of TP. So smooth toric surfaces are either a iterated blow up of P2 or an iterated blow up of the Hitzbrook surface. And basically, what we have to do here is characterize those guys that are an iterated blow up of the Hitzbrook surface, but not P2, and then show that on those guys you can never find a divisor such that it is stable. And then we could have also had the following theorem. So that was independently proven by this Gupta. They can. And also, and the same thing holds for varieties of precovering tools. So if X is toric variety, toric rank 2. So then by the theorem of Klein-Schmidt, they will all look like this. They look like X is some projectivization of OPS plus OPS of A1 plus and so on. OPS of AR. So then we can assume that A1 orderly, then Tx is stable with respect to some D, if and only if X is the blow up of Ts at some weight, and in that case, we have that A1 AR is equal to 0, 0, 1. And this is complicated. We can describe the locus of stability also, like the line bundles for which this is stable. In general, it's not going to be true that it's stable if and only if the blow up of a projective space. So there is an example of a four-dimensional Fano variety that the tangent bundle is stable, but there is no map to B4.
So Milena, is that a blow up in a point of PS, or is it something else? Because we can't really read it.
I think it's a point.
What did you write?
What did you write is the question.
Might be something, could be maybe a bigger thing.
You just completed.
Yeah. Yeah, there's a reason you complete it. Okay, so like, this is an example. I can't think it through now. X and dimension X equal to 4, X cubed. Toric smooth panel, and no morphism. To P4 plus Tx stable. So this is not, this doesn't work in higher dimensions. We don't know about dimension 3 actually. Okay. So I wanted to talk a little bit more about the Fano case. So with X Fano, I said like before, you know, because of this condition to the existence of Keller-Einstein matrix, people have studied this a lot. So finally in dimension 2. So they've had two surfaces. Of course, as we have seen, now have stable. So there we looked at stability. We only care about stability with respect to minus kx. Oh, I think I didn't make that clear before. So what I said before, the Kobayashi-Lübke theorem says that it's fully stable with respect to minus kx, the anti-canonical model. So if you have a Keller-Einstein matrix, then let me see here. Yeah. Yeah, sure.
So just for a sanity check in the previous theorem, so Tx is stable with respect some divisor if and only if x is a block at some p. But then I suppose that means that x must be in the some projectivization of O plus O1, like just two.
In that case, it's the projectivization of OO. So in that case, it's P of OPX to the R plus OPX.
But the dimension, does the dimension check out? Yeah, the dimension must be the same as S, right? So the dimension is S.
The dimension.
Because it's directional to Tx?
No, the dimension here is much bigger than that one of S. The dimension of this projectivization is much bigger than that of S. It's S plus R.
Minus 1. No, it's a plus. Okay.
S plus R because of the minus 1.
No, but it's a plus. It's a plus. Yeah.
Yeah. Yeah.
Maybe I'm a bit confused. How? So if x is equal to this thing, how could it be also above? So x is this projected bundle. And
Projected bundles can be blowouts of things. Yeah.
But of PS.
Yeah.
How could we get something that's like much higher dimensional? Like not blowing up.
Yeah, that's my question.
I guess the R is
Are the two
one
S's
when
the same?
X is a block.
Milena, are the two S's the same? Is that the question?
Sorry. Yeah, so this must be a different. This is not the same as this is going to be some S prime. Yeah, thank you. Yeah. Okay, so if they got headsels, then Tx is stable. With respect to minus Tx. And in the three-dimensional case, so that was 98, and the three-dimensional case Steffens, in 96, he classified when Tx is stable for Thanos of dimension 3. And this was okay. Then hold on. In 21, they looked at toric funnels dimension 4 and Pythagoras 2 and classified that these are stable and just looked up the 20 toric funnel dimension 4 Pythagoras 3. Okay, and then my student wrote a program. So in dimension 4, toric funnel, there are 124 toric funnels and 470 for the tangent bubble. Unstable. Unfortunately, I don't know at this point for which one is semi-stable and for which one is stable. So there is a question is, can we somehow relate this to geometry? And unfortunately, there's also a negative answer, but maybe there's, I don't know, would be nice to fix this somehow. So, so there's what is the relationship to geometry? So there was a conjecture by Milena, the beginning of the 2000s, and that's based on this work of Steffens here. So we look at this and try to find out what does it mean that they're stable. So if X is a smooth funnel, such that Tx is unstable, then we sort of want to find out why is it unstable with respect to minus kx. So then you thought then there exists contraction y from x to y of an extremal phase of the Morricone of curves. So many contractions one sees a lot is you contract over way of the Morricone. Here we are allowed to construct complete phases of Morricones. So with dimension y is less than the dimension of x, such that the relative tangent tangent sheaf T phi. So this is defined as follows. We have a map from Tx to phi upper star Ty, and so the relative tangent phase is defined as the kernel of this map. destabilizes Tx. So in Picard rank 1, there was also a conjecture. So what does it mean in Picard rank 1? Well, we can't have any Morgan contractions in Picard rank 1. So that means that in Picard rank 1, the conjecture should be that the tangent bundle is stable for Picard rank 1 Fano variety. And that is like what's the folklore and conjecture attributed to Miskowski. And so there was already I need to give a counterexample to this. One. So this is a horospherical variety. It has a bunch, but yeah. The smallest dimension is 4. Sorry, 12. And Reynolds gave a counterexample in dimension 4 and Picard rank 4. So that was 4. This was one of these toric Fanos, a smooth toric Fanos of dimension 4. And the funny thing was there were 82, right, with unstable tangent bundle. Oops. I think my numbers are wrong. I'm sorry. Anyway, so amongst all of these ones with unstable tangent bundles, so there was only one where this conjecture fails. So it's sort of almost right, but it's not quite. So only one. I will look up the correct number in the break and give it to you. So of course, I mean, there might not be a geometric explanation why the tangent bundle is unstable or not, but I mean, I don't know. It would be nice to find one. So I'll end with this, and in the next half, I'll talk about sort of what are the methods that go into proving stability for toric vectors.